I think we'll probably finish chapter 15 right now. We got as far as introducing amines and naming simple amines. And I said, keep it simple. And here, I think on this next slide is a pretty good example. Here is what I suggested you call this. There's an ethyl, it's diethylamine. Now, this is pretty complicated. We haven't gotten to this yet. We'll get to this right now. That's your IUPAC name. But this is a simple amine, so just learn one name for it. And actually, most organic chemists would appreciate it if you called it diethylamine, even more so than if you used an IUPAC name. So let's go ahead and name these. Go ahead and name these. Yeah, everyone but this one. All of these are simple amines, except this one. Even that one, we could try to name it simply. Well, let's do the simplest first. What's that? This one here.
Methylamine.
Methyl. All right, let's have a different row. That row there, what do you call this one? Dimethylamine. I don't think we named these yet, did we? This row. Someone in this row. Name this one. How many carbons we have there? 3. No, it's no try. It's 3 carbons would be propylamine. Just propylamine. All right, over here, we got the 4 of you. Someone over there. Top one. Diethyl. Okay, what does that leave out? You got a good start. Ethyl, diethyl. Diethyl, methyl, amine. Diethylmethylamine. Remember, you got to bring everything into the name. Diethylmethylamine. All right? It brings everything into the name. Got 2 ethyl groups and a methyl. This row. Got it, Trevor? Methylpropylamine, and that would be alphabetically. Methylpropylamine. Remember, if I gave you that name, you should be able to draw it. How would you do that? Well, you know that an amine is going to have 3 things coming off of it, and if one of them is a propyl and one of them is a methyl, then you know the third one has to be a hydrogen. This one up here, diethylmethylamine, there's going to be no hydrogen on it. You got your 3 groups on the nitrogen. All right, so be able to go from a structure to a simple name, or from a simple name to a structure.
And if there's no hydrogens, that would make it a tertiary. If there's
right.
1, it would be secondary, and if there's 2.
Yeah. Yeah, that's coming at it a different way than what we said it. I think that would always work, but the definition that was given is count the number of carbons that are attached to it. So one carbon is a primary, and we did this exact same slide earlier on when we classified them. So we said that was a primary, one carbon attached to it. This is a secondary amine, primary amine, tertiary amine, because that's 3 carbons. What I was trying to think if what you said would always work.
Not if there's a substituent.
Yeah, well, if there's a substituent group, I think it would have a carbon. So I think what you're saying would always work. The primary does have 2 hydrogens, but has 1 carbon, 2 hydrogens. But maybe counting the carbons gets you right to this number. 1 carbon, primary. 2 carbons, secondary. 3 carbons, tertiary. So it's lining up that way. And I mean, we could probably call this butyl ethyl methylamine. I probably could, but it would leave a little bit of ambiguity because that the nitrogen could be attached right here. So once it gets above 3 carbons, I'm saying abandon the simple and go to IUPAC. Treat it as an amino group. All right, now I want to use this molecule as an example here. Number one, I say you should know this molecule. Whenever you see a benzene ring and you see a new functionality come up, you probably is one you need to add to your list of benzene derivatives. So this is an amine functional benzene, aniline. And I want to use that as an example here to show you something. I'm going to put down 3 molecules here. Aniline's going to be the first one. So there's aniline. There's aniline, but we've got a methyl group attached to that nitrogen instead of 2 hydrogens. Here is aniline. We're going to have a methyl group attached to the benzene ring. Now, this is aniline, so this is where you're going to start counting carbons. Carbon 1, 2, 3. So this would be 3 methyl aniline. Nothing real surprising about that. We've used numbers throughout the course here to indicate where these substituents are attached to the organic molecule. So the methyl is attached to the carbon number 3 on that benzene ring. But over here, we've got aniline. And we have a methyl group. Where is it attached? This is 1. No, we're going to use an N instead of a number. It's N-methyl aniline. So it's actually telling us the methyl group is on the amine. It's on the amine functional group that's on that molecule. It's N-methyl aniline. I mean, these two things here are isomers of each other. You got a methyl, but you have it in two different locations. One is located on the nitrogen, one is located on the benzene.
Earlier we were using OMP to classify aromatics.
Yeah.
So for nitrogen based, we're getting back to number.
Well, no, that's not either. That's not in the ortho, meta, or para position right there. It's on the
Right, but
nitrogen.
on 3-methylaniline.
Well, we could also call this meta. Here's your ortho, meta,
Right.
para position. So you could call this meta M-methyl aniline.
Which are you going to call it?
I would probably call it 3-methyl aniline. Even when we used the ortho, meta, para, I was just saying that is a traditional naming system,
Okay.
and there is an IUPAC. So you don't have to use OM and P.
Gotcha.
But you need to be, if I gave you the name of a molecule like, like parachlorotoluene, you'd need to be able to draw that. We're getting a little bit off the track, but that's okay. So parachlorotoluene, this is toluene. Yes, just shake your head, yes. You will. You should. Para means there's a chloride right there. A chloro, not a chloride. Chloro group right there. This is the ortho, meta, para position. It's a little sloppy, but ortho, meta, para positions. Para is opposite. Completely opposite, other side of it. Or that would be 4-chlorotoluene. It has both names. Okay. Now I just want to make it clear, I'm not just using this because we're dealing with aniline. Let me give you another molecule to just show you that when you have a methyl, or when you have a substituent on the nitrogen, you use a capital N, just like you would use a number to say something where something else is. So let's take a chain here, just something like this. Let's put in a amine right here, and let's put an ethyl group right here. So we got an ethyl group right there. So name that. Go ahead and name that molecule. This isn't aniline. So So 5 carbons would be pentane. It's an aminopentane. What amino? 2 amino. And there's an ethyl. And the ethyl's not on the pentane, is it? Yeah, N-ethyl. Okay, now N-ethyl 2-aminopentane. And here I've kind of reordered the name, where ordinarily I said we're going to put the miscellaneous thing out front, and then the alkyl groups in the middle, and then the parent name on the end. And I'm kind of scrambling this up a little bit, but I do and I'm not actually really sure, but I'm pretty sure this is the way you would most commonly see this name. Why? Because the ethyl, see the way we're writing it here is it's N-ethyl 2-amino. Where is the ethyl? It's on the amino. It's not on the pentane. This would be acceptable, and it would be in line with what I've been telling you. Miscellaneous alkyls, parent name. And I'm kind of breaking with that because this is not on that. This is on that. So it's N-ethyl 2-amino pentane. Would I accept both those names? Yes. Would I draw the same molecule from both of those names? Yes. If I went to draw this molecule, I'd draw a 5-membered ring, a 5-carbon chain. I would put an amino group. I would put a nitrogen on the second carbon. Yeah, if I was going to draw that, 1, 2, 3, 4, 5, I'd put a nitrogen right here. I'd say that nitrogen's got to have 2 more things on it. Oh, it's got an ethyl, and it's got a hydrogen. So I would draw the right molecule. Those are both superimposable. I usually write from left to right and then do it. So yeah, I would go to that structure from either one of these names. Okay, and I just want to make the point that we're not just using that with aniline or aromatic amines. We're just in general. If you've got a substituent on a nitrogen, on an amino functional organic molecule, this is what you do. Don't use a lowercase n, use a capital N. Capital N. We don't want it to get mixed up with meta or anything else. Ortho, meta, para, usually lowercase letters, but this would be an uppercase. Let's see, I think the previous slide had, so yeah, it shows you some of those examples. So here's N-methyl-aniline. Here's 2-ethyl N-methyl-aniline. I guess yeah, okay. They're just alphabetizing them here. N-ethyl N-methyl-aniline. So here you have an amine that has 2 substituents on it. If it had 2 methyls, if there was another methyl here, and that wasn't there, then you would NN, dimethyl. Just like if we have 2 methyls on the same carbon, it's 2,2-dimethyl hexane or whatever it is. You have 2 of these, you need to have 2 designators as to where they are. All right, aniline or benzamine, but 99% of the time that is going to be called aniline. You don't need to memorize that molecule, but there's toluidine. You got the cross between toluene and aniline is toluidine. There are some other common names out there, but you don't need to, that's not that common. Physical properties of amines. The nitrogen has a fairly high electronegativity. You have an attraction of the electrons to the nitrogen, forming a negative concentration here, positive at the proton, and you can get hydrogen bonding from nitrogens to hydrogens. So they are polar, not as polar as alcohols. So if you looked at that, that's methylamine. If you compared that to methyl alcohol, these two would have about the same molecular weight. All right, you got carbon and a nitrogen, you got a carbon and an oxygen. They're right next to each other. They're very similar weights, and even the nitrogen now has 2 hydrogens on it. The oxygen only has 1. So very similar molecular weights, but the methanol would have a higher boiling point because it hydrogen bonds more strongly to another methyl alcohol molecule than the methylamine does to another methylamine molecule. Binds more strongly, takes more energy to break that attraction. All right, when we do that, we're not breaking a covalent bond. We're not busting up the molecule. We're just disrupting that attraction between molecules. Hydrogen bonding. It's not as strong as a covalent bond, but it is extremely important in biological systems, this hydrogen bonding. DNA helix is held together by hydrogen bonding. I mean, the individual strands are covalently bonded, but the 2 strands of DNA are held in position by hydrogen bonds. So they're not as strong as the covalent bonds, but they can be broken, they can be spread apart for replication and come back together again. So hydrogen bonding is really an important little thing in biological systems. Really important. Enzymes. Substrates are coming into the active sites of enzymes. They're hydrogen bonding into those sites and then chemically being acted upon, and then those bonds are breaking and they're moving away. So it's great that they're not real strong bonds, but they are very real attractions. All right, because the molecules are polar and are attracted to each other, they are attracted to polar molecules like water. So amines will have some solubility in water, more so than an alkane. But just like the alcohols are soluble in water, and as the alcohol chain gets longer, the alcohol's solubility decreases, you would find the same thing with amines. As the 2 carbons, 3, 4, 5 carbon long amine would become less and less soluble in water. Amines smell like rotten fish. They smell like. So rotting fish give off these low molecular weight amines. That's why they smell that way. So rotten fish smell like amines, or amines smell like rotten fish. Which one came first? I don't know. Maybe the rotting fish. Preparation of amines. I'll just kind of mention this. Reduction of amides, and we haven't talked about amides yet. We will in a minute, but here's an amide. If you can reduce it by hydrogenation to an amine, or you can take something like nitrobenzene and hydrogenate it and form an amine, aniline. Let's see. The 3 most important reactions is for amines: dissociation, neutralization, and preparation of quaternary quat salts. There's some similarities between these 3, but these will probably be the 3 things I want you to understand about amines and how they react. Dissociation, just keep in mind that amines are weak bases. All right, so let's do number 1, dissociation. This is a little bit of review. Ammonia plus water. Remember, you learned ammonia is a weak base. So if you put ammonia in water, ammonia is a proton acceptor, and it will form the ammonium ion. This is ammonia. This becomes ammonium. So what's left over? If the ammonia gets a proton from the water, what else is left? What's left over from the water molecule? An OH. All right? And what is OH in water? Basic. It's what makes the water basic. High hydroxide ion concentration makes a very low H plus concentration and makes it pH greater than 7. So this is a weak base. Well, if I took something like methylamine, instead of ammonia, now I got methylamine. Plus water. Instead of NH4, because there's a methyl on there, I'm going to have an NH3 with a +1 charge on it. And OH. So this is NH4 plus is the ammonium ion. This is going to be the methyl ammonium. Ion. Methyl ammonium ion. Or if you had something like this, that would be methyl ammonium hydroxide. What I have there on the bottom, methyl ammonium hydroxide. Just as this is called ammonium hydroxide. Right? That's ammonium hydroxide. That'd be methyl ammonium hydroxide. This is a +1 ion. It's a -1 ion. It's a salt. Or no, it's not a salt. It's a weak base. It's a base. All right. Now, some of you in the back of your mind, it might be bothering you. I said, hey, nitrogen only binds to 3 things. When it binds to the 4th thing, it's going to get a +1 charge. It's not a compound anymore, it's an ion. So, I mean, you saw this in 1305. Nitrogen it's bound to 3 hydrogens, and it is associated a proton to that lone pair of electrons, making for a +1 charge. So we're going to see a couple more examples here where nitrogen now has 4 things around it, and whenever you see that, it's going to have a +1 charge. Doesn't have a +4 charge, has a +1 charge. The NH3 itself has no charge, neutral. That's neutral. You add 1 proton, now you've got 4 hydrogens, but you've added 1 proton, and you got the +1 charge of that proton. Yeah, it's a proton acceptor.
Electronegativity difference between hydrogen and nitrogen, is it just got negative charge there?
Actually, the oxygen has a higher electronegativity, but it is in very high concentration. So we're shifting the equilibrium in this direction, getting a little bit of this, some of that. You don't get a lot of this. You don't get a lot of this, even though there's tons of water. You could have, you could have, let's say, 3% ammonia and 97% water. You're going to get a little bit of this, but you got a ton of water there. It's shifting the equilibrium this way a little bit. That's a good question. Not very far. 99% of your ammonia is in that form. You get a little bit of this, but it does raise the pH. Weak. Sodium hydroxide will have a pH of about 13. Windex, which is ammonia in water, is pH of about 9.5. So it's not a real strong base. It's a weak base. These are weak bases. All right, why don't you name this? Yeah, name. See what's happening here. Let's say we took that molecule and put it in water. What would we form? Let me just help you out here. This looks like this. How many hydrogens will be on the product? To the right.
The whole compound, or the whole molecule?
Yeah. Oh, okay. You're right. 10. Yeah, we'll only get one more hydrogen right there, right? But we had 9 hydrogens to begin with. Yes. 10 hydrogens. And what charge? +1 charge. And what name? What?
Dimethylamine?
How many methyls?
Oh,
Trimethyl. Trimethyl ammonium. The product will be trimethyl. It's be the trimethyl ammonium ion. Trimethyl ammonium. Okay. Okay, reaction number 2 is neutralization. And here's an example of it right here. An amine plus HCl forms a salt. I just got done showing you that amines are weak bases. Bases react with acids to form salts. They usually react to form salts and water, but we're not going to get water in this case. We're just going to get this salt. Propylamine plus hydrochloric acid, propyl ammonium chloride. Propyl ammonium chloride. You see we've got a carbon and then we have 3 hydrogens coming off of this nitrogen. We've got 4 things bound to the nitrogen, which it then acquires a +1 charge. the chloride is attracted to that positively charged ion. You get this salt, ionic salt. All right, this is neutralization. An amine, and probably the only thing I'll really be reacting it with is that acid, hydrochloric acid, and we'll get an ammonium chloride salt. It's some sort of ammonium chloride. This is propyl ammonium chloride. Just come right off of this name, propylamine. Change the amine to ammonium, and you've got the name of the salt. Add chloride to it, propyl ammonium chloride. Now, any of you taken any kind of a nutritional supplement, not any kind, but amine functional ones, like lysine, or if you're taking a prescription drug, oftentimes what you might find on there, many prescription drugs have amines. We'll show some biologically active amines here in a minute, bunch of examples. They will, you might see it on there, it'll say active ingredient, hydrogen chloride. Hydrogen chloride, I don't know if you've ever noticed that on a label. But what they've done is they've taken the active form of the drug and they have reacted it with HCl to convert it into this salt. And the reason they do that is that this salt will be more soluble in water than this is. Now, why would they want something you're taking orally to be more soluble in water? What would that result in? If it was more soluble in water, higher, it would absorb into your body more readily. More percentage of it would, be bioavailable. In this form here, let's say I'm not even saying this is a drug you would take. But if it was, your body might absorb 50% of this, but it would absorb 75% of that. So if they actually want you to get 300 milligrams, I'd say, you're going to have to take 600 milligrams of this to get 300 milligrams of it in your body, where you might only have to take 400 or 500 milligrams of this, and you'll get 300 milligrams in your body. Bioavailability. Yeah, so many things. You get a prescription. There's probably an NH2 on there somewhere. There may be a couple of them. It's not that you're taking an acid. It's not that it's acidic. It's been neutralized to this. They've probably washed it and adjusted the pH, made sure there isn't excess HCl in there. They have it in this salt form. But they've converted the amine into the ammonium chloride. Okay. Now, a minute ago, I had you take, we want a nitrogen here. I had you take trimethylamine, and we reacted it with HCl. Yeah, let's do it this way. We've got this plus HCl. So this thing right here plus HCl, and you got the trimethyl ammonium chloride. Now what do we do? We reacted with HCl. This instructor needs better penmanship. Here we're going to react it with methyl chloride. Methyl chloride, not HCl, but methyl Cl. The methyl is going to go on the nitrogen, form a +1 ion, and the chloride. So now quat, we have, this is a quat salt. We've got a nitrogen with 4 carbons attached to it and a +1 charge. So these are quats or quat salts. All right, so they don't all have to be methyls. Usually 3 of them will be. And then this could be something else. I mean, you could have this sort of thing, and then maybe a methyl, and a methyl, and it's still going to bear a +1 charge. So that would be trimethyl propyl ammonium chloride. Trimethyl propyl ammonium chloride. There's tetramethyl ammonium chloride. Got 3 methyls around it. I mentioned to you that I used to work at Dow Corning, and back in probably the 60s or 70s, I'm not exactly sure when this happened, maybe even the 70s and 80s, there was a person there working in research, and he was playing around with these quat salts and associating them with some silicones, coupling agents, so that you could actually attach them to things. He had a dog. He went to the vet, and he's sitting there with his dog waiting to be the next patient. And the waiting room had a foul odor of all these animals that are coming in and out of there. And so he started working with the vet, and he says, I think I might have something that'll be able to knock down the odors in your waiting room. And so he started playing around with these quat salts and applying them to the walls and the ceilings and all that sort of thing. And lo and behold, it really did cut down on the odors because it killed the bacteria. These quat salts will kill bacteria. So that ended up spawning, I mean, you think, oh, what about vet offices? Well, the people who really liked this were hospitals. They started treating the walls of operating rooms, treating the walls of the hospitals, the hallways and everything, treating them with these quat salts that are actually bound to the paint, bound to the ceiling, and it actually cut down on the bacterial load. And I'm not sure if they still do that. I think they probably do. But it spun off a business. They sold that off to people that started going around applying this. The product was DC 5700 antimicrobial emulsion. I remember I worked at the plant that produced it. DC 5700. And I imagine it's still going strong. Oh, the other place where you might have come across it, gym socks, BioGuard socks. Have you ever bought BioGuard socks? Sometimes there's a sock that have a little line on them. It'll say BioGuard, reduces odor or whatever. On socks, they put it on carpeting, so carpet manufacturers would use it. I think other places, because it'll bind to fabric, it'll bind to paint, it'll bind to ceilings, it'll bind to tables, but if you scrub them, it'll braid off of there. So you can't necessarily kind of do a countertop and expect it to stay that way. It'll braid off, but you can treat lots of things with these quat salts. What they're doing is they've got a see, what would they have out here? OH groups on the silicone, and then you'd have carbons going off to one of these quat salts. I don't know exactly the formula for A5700, but it's something like this. And this actually will chemically bind to the paint. This silicone cross-linker right here will attach itself to the paint with covalent bonds so that it is not just on the surface, it's actually chemically bound to the surface. And so you got hanging on the surface of your paint these little quat salts, and bacteria can't propagate on that surface, on that material. So these are antimicrobial.
Is that because of why can't they?
I'm not sure. Somehow that affects the bacteria. I'm not sure. I should get a little bit of this and see if the micro classes could play around with it. I probably would have a hard time getting it, but try. But that's quat salts, and you're going to see the quat salt come up here, like right here. These are biologically relevant molecules. Choline is a quat salt. Acetylcholine, what you've done, you've just put an acetyl group. You've turned this into an ester. Here's an alcohol. React it with acetic acid. You get acetylcholine, quat salt. +1 charged. These are neurotransmitters. So these are biologically active molecules. Very relevant. This just mentions why we convert them into the salts for bioavailability. Terminology, heterocyclic amines. Here's probably the easiest one to look at. You basically got a benzene ring, but you replace 2 of the carbons with nitrogens. It's still aromatic. It's a pyrimidine ring, purine ring. This is the basis for adenosine. So adenosine triphosphate. Adenosine has a purine ring. Look at 4 nitrogens in a fused ring, 2 fused rings. So your ATGC bases in DNA have these heterocyclic amine rings. Yeah, vitamin B6 or niacin, NADH. All right, we'll just talk about amides for a few minutes here. Any questions about amines? Okay, I covered those 3 reactions: basicity, neutralization, and quat salt formation. All right, so those are the 3 main reactions in chapter 15. Amides. There's your basic functionality for an amide. You got a carbonyl with a nitrogen on the carbon that has the carbonyl. And that's an amide. A biochemist would call this an amide bond. A organic chemist would call this an amide, which is what we're calling it. A biochemist would call it a peptide bond. So the backbone of protein is this backbone. It's carbonyl, nitrogen, carbon, carbonyl, nitrogen, carbon, carbonyl, nitrogen, carbon. That's the peptide backbone. So a peptide bond is an amide bond. I think the best way to approach this in terms of naming it is just count the longest chain. Just do it the way we've been doing it. Count the longest chain, including the carbon that has the carbonyl, 1, 2, 3, propane, drop the E, and add an amide. So let's just propane, drop the E, propanamide, propanamide. They're presenting it here. It's being presented here on this slide. You can see when I don't like something, it's always they that are doing it. It's my slide. So this slide, they're approaching it from the point of view of what would you call that carboxylic acid. You can do it any way you want to. You can make this amide by reacting propanoic acid with amine, with ammonia. You would get propanamide. So you're reacting it, but if you're just looking at an amide, just say 1, 2 carbons, so that's ethane, ethanamide. And I'm not going to, here's the ones that I would like you to know, just these two basically. Well, there'll be one more. I'll give you that one to you here in a second. So methanamide, 1 carbon, there's methanamide, but it's also formamide. You should know the common name of that, formamide. You know formaldehyde, 1 carbon. You know formic acid, 1 carbon. And now formamide, 1 carbon. And then here's 2 carbons, ethanamide, also acidamide. It's probably called acidamide more than anything else. And then the third one, I'm going to give you the name, and you draw it. Benzamide. So here's a benzene ring. What should that look like? Pencil do you have? Just a pencil?
It's the iPad pencil.
Oh, okay.
Yeah.
Can you erase?
Mm-hmm. If I just stop this and just do that.
Okay. Benzamide. There you go. Yep.
So the hydrogen would be
Where?
so this would be the bond from hydrogen?
No, there's none of me. Yeah,
Okay.
but that's got to be aromatic.
Okay.
You got it? No, now you have, that's aniline. That's aniline. Okay? Okay, this is different. So the amide, so benzene is going to be like that. The amide has to have this and then this. Benzamide. All right? So you have to have the carbonyl and an NH2 on the carbonyl carbon. So yeah, if you had benzoic acid, which maybe you forgot it because benzoic acid, you reacted that with ammonia, you could break off a water molecule here, so plus ammonia, you could get benzamide. That's why they're kind of taking you from, so you get an NH2 on here plus water. Keep in mind NH3 is NH3 is NH3. So you can see how you can react. You can react to carboxylic acid with an amine or ammonia and make an amide. So there's your water. Splitting out water, and you're bonding this NH2 now is taking the place of the OH. The NH2 is taking the place of the OH. And a benzamide. I'll just quickly go over this. We don't need to worry about this too much. Yes, there's some. You got on an amide, you have an NH2 group, which you have polar bonds. Carbon-oxygen bond, there's some separation of charge. So a hydrogen on the NH2 can hydrogen bond to the carbonyl. So you get some polar attraction of molecules, some water solubility as a result of that. We won't worry about this. Amides you can hydrolyze them with a strong acid to get your carboxylic acid and an amine, or react them with a strong base, and you would get a salt and an amine. Pretty much comparable to the ester reactions, except there's no amine involved. You get alcohols instead of amines, but it's comparable to the acid hydrolysis of an ester and the base reaction with an ester. All right, just to show you the breadth of molecules that are biologically active that are amines. Dopamine, neurotransmitters, epinephrine or adrenaline, norepinephrine. So norepinephrine would have a hydrogen here instead of a methyl group. Norepinephrine. Okay, so norepinephrine is a whole lot like this, except it doesn't have that OH right there. These are all neurotransmitters. Serotonin, histamine, acetylcholine, we mentioned earlier. Antihistamines are trying to suppress the release of that molecule. Histamines, which what is an inflammatory response? Your body gets something that it doesn't like, allergic reaction, it starts wanting to, it starts this inflammatory response. So antihistamines are suppressing that to try to suppress that response. Morphine, codeine. So you can see the nitrogen functionality in these. So that would be like a tertiary amine right there. Codeine, heroin. Heroin and codeine, pretty similar. Well, some differences. Caffeine, nicotine, nitrogens. Nature loves nitrogen. Some methamphetamine right here, N-methyl-1-phenyl-2-propanamine. Methamphetamine. Yeah, so here's amphetamine, and now you've methylated that nitrogen right there. Put a methyl on that nitrogen, you got methamphetamine. Novocaine, Demerol. Here's some decongestants. So I assume synthetic synthetic molecules. Many of the others were naturally occurring. Ampicillin, nitrogen all over the place. There's an amine on a sulfur, and all of that is on aniline. So here's your aniline in the name, sulfanilamide. Sulfanilamide. It's not an amide. It's a instead of carbon oxygen double bond, you got a sulfur oxygen double bond. Yeah. Artificial sweetener, aspartame. You've got an amide link holding two amino acids together. This is a modified amino acid. It's not phenylalanine in its normal, natural state. It's have this ester linkage on there. Ordinarily, that would end with an O out here, phenylalanine, but they've got made the methyl ester of it. Okay, here's a summary of reactions. And so this reaction, and the quat reaction. So a tertiary amine. To make a quat salt, you need to start with a tertiary amine plus methyl chloride. Forms the quat salt.
Is it always chloride, or can it be any halogen?
It could be any halogen. It could be methyl bromide, but it usually would be chloride. For anything biologically active, you wouldn't want probably anything else in there. And if some of you remind me, there's these slides before the exam. We could come back. There's a summary of all the reactions for chapter 13 and 14. That reaction quiz will probably be chapter 12 reactions, 13 and 14. That's what the reaction quiz will be over. It won't be over amines. It will slip back into chapter 12, alcohols, aldehydes and ketones, and carboxylic acids and esters.